Hello, this video will show you an easy proof of the Pythagorean theorem. This theorem relates to any right triangle, and it states that in a right triangle, the square of the length of the hypotenuse is equal to the sum of squares of the legs of the triangle. In the picture, there represented a right triangle with sides 2, 3, and 3.5 units. As an example, the vertices of the triangle are capital A, capital B, capital C, and the corresponding sides are A, B, and C. We are going to prove in this video that A squared plus B squared equals to C squared. For the proof, let us draw the square with a side of the leg A, CBDE, the square with the side leg B, CFGA, and the square with the side of hypotenuse C, AHIB. Since a square is a such geometric figure which has all its four sides equal to each other, and all its four angles are right angles, and the area of a square is equal to the square of its side, the area of the square CBDE equals to A squared. The area of the CFGA equals to B squared, and the area of AHIB equals to C squared. Now we have to prove that the sum of the areas described on the legs A and B equal to the area of square built on the hypotenuse C. For this, let's make additional constructions. Describe around the square AHIB another square MNOC in such a way that vertices of the square AHIB, which are AHIB capital, lie on the sides CM, MN, NO, OC correspondingly. For that, just draw straight lines CO over CB, straight line CM through CA, line MN perpendicular to CM through point H, and line NO perpendicular to CO and perpendicular to MN through the point I. Now we can see four equal triangles inside of the square MNOC. They are triangle MHA, triangle HNI, triangle IOB, and triangle BCA. Each of them is a right triangle with legs A and B and the hypotenuse C. I leave for you to prove that these four triangles are equal to each other. If you will need a help with this proof, please write in comments and I will prove it for you in the next video. Next, let's draw another square through line segments GA, GF, DE, and DB. Then we obtain the square GKDL. We can see inside of GKDL square GACF with a side B, square CBDE with a side A, and two rectangles FCL and AKBC. Rectangle AKBC is divided by AB for two equal triangles, ABC, which is our original right triangle, and triangle AKB. If we will draw the diagonal FE in FCEL, we will obtain another two triangles, FCE and FEL. They both are right triangles and equal to each other. Moreover, all four triangles in this square are equal to each other and have legs A and B and the hypotenuse C. Prove this by yourself or write in comments for a help. Furthermore, these four triangles and another four triangles in the square MNOC are all equal to each other, and squares MNOC and GKDL are also equal to each other. From this follows that if we subtract from each of these squares four internal equal triangles, then in each square there will be left over areas which are equal to each other, and they are the square AHIB with the area C squared, and the sum of squares CBDE with the area A squared, and the square GACF with the area B squared. This completes the proof that C squared equals to A squared plus B squared in a right triangle.